Welcome to the Christmas session of the seminar. Our speaker today is Jan Volec, who is a postdoc at McGill University and was postdoc at ETH Zurich, and he got PhD from University of Warwick in UK. And he'll be speaking about degree thresholds of cycles in oriented graphs.
Okay, thank you, Bernard, for the introduction. So, thanks to all of you that you really come here on Saturday. I hope I will help you to survive the weekend and not like ruin your weekend. Anyway, so yeah. So first of all, I should mention that all what I'm going to talk about today is a joint work with Roman Glebov, who is currently at Hebrew University in Jerusalem, and with Andrzej Grzesik, who is based in Krakow, Poland, but he's currently for a year postdoc in Warwick in the UK. Okay. So I want to talk about degree threshold cycles oriented graphs, but before I will start, I really tell you the problem that this project was about. Let me start with some introduction and with maybe sort of explaining what words like threshold, cycles, and oriented graphs mean. Okay, maybe some of them are sort of self-explanatory, but anyways, what I want to start with at the beginning is an old problem and still widely open problem, which goes back to a conjecture of Caccetta-Haggkvist from late 70s, and it says the following: if you give me an n-vertex directed graph G, or digraph, and by digraph I mean it's fine to have, so there will be no multiple edges, but it's fine to have an arc going from U to V and simultaneously also from V to U. So you give me an n-vertex digraph G with minimum out degree at least K, and then Caccetta-Haggkvist conjectures, then you should be able to find an oriented cycle of length at most n over K, maybe ceiling of n over K. And if one thinks about it, this is sort of like a qualitative generalization, or well, no, not quantitative generalization, or quantitative strengthening of the simple observation that if you have a directed graph and every vertex has an out degree at least 1, then since the graph is finite, you must enclose a cycle. And indeed, if K is 1, then all of this is saying that, okay, if out degree is at least 1, you find a cycle. But then it says, but then the conjecture says, I guess I will change the sign because of the cables, I'm sorry. But then the conjecture says, okay, as long as you can assume something stronger, then also you can deduce something stronger, meaning a cycle of shorter length. And there are kind of two ways how to think about it. Either you think that indeed you provide me a better bound on out degree, and then you try to squeeze as short cycle as you can out of this assumption, or on the other hand, you fix the length of the cycle, you fix the length of the longest cycle you are interested in, and then you are trying to push the minimum degree, forcing it as low as you can. And those two problems are really the same problems, just you are looking at it from the two different angles. So what is known about the conjecture? So, for instance, it's known that if you sort of go with K being K being rather slow, like this kind of regime when K is 1, you get a cycle and so on, then the conjecture is true. And as far as I know, the best result in this direction goes to Shen and the beginning of 2000, where he showed that the conjecture is true as long as K is at most square root of n. On the other hand, if you go to the other extreme, this seems to be like this seems to be the instance of the conjecture which is really difficult, and more or less, we really don't know how to approach it. So, okay, maybe just a side remark. It is stated as for digraphs, and it allows the parallel edges and so the parallel arcs in the opposite direction and loops in the way as I stated it. But since I really care about cycle of some bounded length, as long as I would have those parallel edges, I would be in a good shape, and as long as I would have a loop, I would be in good shape. So let me just move to the situation where I have an oriented graph. So I get a simple undirected graph, and I take some orientation of it. And then the case when I plug here a triangle, the fact that I'm interested in triangles, says that, or reduces to the following statement. Caccetta-Haggkvist conjectures that if you have an n-vertex oriented graph where every out degree is at least n over 3, then you should contain an oriented triangle. And unfortunately, I won't really say anything towards this conjecture. Maybe I will mention a bit, but really nothing. But before moving on, let me just say here and also show you sort of one of the phenomena, and use this as a good example, that if the conjecture is true, then it is indeed best possible, and you cannot improve this n over 3 for very many reasons. Okay, so in other words, I will now show you some examples of graphs that are having out degree just a little bit or just one below n over 3, and they will still not, and they won't contain any cyclic triangle. Okay, this one is sort of a boring one. If you take a 4 cycle and you plug the numbers in, you realize, okay, A, 4 cycle doesn't have a triangle, and B, it is just a little bit below 4 over 3, all the out degrees. However, you can generalize this in a sort of a natural way, that you can always take 3k plus 1 vertices, and each vertex, and you put them on a cycle, or you put a cyclic order on them, and then each vertex I, you connect modulo 3k plus 1 with the vertices I plus 1, I plus 2, all the way up to I plus k. So in this way, every vertex will have out degree exactly k, but the numbers are tuned up in a way that there is no way how you can loop around this whole cycle 3 times to arrive where you started. So, okay, and this is, for example, the appropriate graph and k is equal to 2, but you can do more. I think it was Bondi who observed that if you would have 2 graphs that are tight for Caccetta-Haggkvist, and you do their appropriate composition, or sometimes people you take their lexicographic product. So what does it mean? You take your graph G. Let's say that graph G, which would be tight for the Caccetta-Haggkvist conjecture, is the 4 cycle. You blow it up, which means each vertex you replace with an independent set of size L, and then between 2 blobs of size L, you direct the edges as the original graph G was stating about the original pair of vertices. And now inside each blob, you put copies of the graph H. And then one could observe that in this way, if I start with something that has out degree around n over 3, I will still have out degree around n over 3. I mean, if both G and H would have those large out degrees, also their product, this product will have large out degrees, and also there is no way how starting from G and H being cyclically triangle free produce a cyclic triangle in this product. So the picture can continue like this, and you can be getting those fractal-like pictures, but you can, as the graph H, choose some other graph than G. So you start like having really you start having exponentially many constructions that would be tied to this conjecture, and you can do even a little bit more. For example, you can take the blow up, but in each of the blobs you can put a different. You don't need to go for this product. You can, in each of the blobs, plant another extremal example. So, and that's one of the reasons why people believe that Caccetta-Haggkvist is a tough conjecture, because of the
Is that true for all values of k, this sort of product construction, or the k equals n over 3?
I sort of have a feeling it works for every k, but I would have to think if I'm not overlooking something simple. But on top of my mind, I do think it works also for other k's, for other values of k. But I would have to think if I'm not overlooking something. I mean, I would kind of expect that yeah, I believe it works for every k. But let me now not think what's the easiest one sentence way how to convince you about it. We can maybe.
It seems right.
I mean, it seems that like there is no way how on the graph G to loop around in a way shorter than k. But once I go inside, I either need to leave, but then I really didn't change my problem, or I spent my time only inside, but then the graph H kicks in. So, okay. Are there more questions? So this is the question of Caccetta and Haggkvist, which was actually inspired by an earlier and weaker conjecture Okay, here I stated it again, and yeah, okay, and maybe for the rest of the talk, I will focus, I will just keep the triangle case of the conjecture, but, oh, okay, I guess, I forgot in which order my slides are going. Anyways, so this is the triangle version of the Caccetta-Haggkvist, and as I said, we really do not know how to approach this conjecture, partially or maybe mainly because of so many conjecture type examples to it. But one can relax the conjecture and try to solve something weaker. And one particular way of relaxing the conjecture, which had drawn lots of attention, is the one where instead of assuming that all the out degrees are n over 3, they would be some c times n for some little bit worse c than just 1/3, for some higher value of c. And actually, already Caccetta and Haggkvist proved one of those relaxations where the c instead of 1/3 was roughly 0.38. Then there was, then in the work of Bondi, where I believe it's also the same work where he observed that the lexicographic product behaves nicely with respect to the conjecture. He improved it below 0.38. Then there were another improvements due to Shen and then Hamburger, Axel and Kostočka. Before the Fleck algebra machinery kicks in, and using the framework of Fleck algebras, which if you do know something about it, then you know what I'm now talking about. If you don't, then maybe we'll wait for another 30 minutes and I will say a little bit more about it. And now just take it as a black box that can do various things in extremal graph theory. Anyway, so using Fleck algebras, Hladký Král and Norin improve the constant even a little bit more. And also, I guess one of the main motivation of Hladký Král and Norin was to actually apply the Fleck algebra framework, because if I remember the historical, that was actually the first non-Razborov application of the framework. And then also Razborov, using the Fleck algebra method, proved that it's a different relaxation now. You go back to the C being 1/3, and you on top of that assume that some other particular configuration don't appear, and then he was able to prove the conjecture. But what is interesting here, that forbidding those three that neither of those three oriented graphs actually appears in any of the tight constructions. So on one hand, this is a simplification and seems to be like sort of an artificial simplification to assume that three graphs also on top of that don't appear. And on one hand, one would say, yeah, you forbid those three graphs to make the proof going through. But on the other hand, it still keeps the difficulty, at least the difficulty that there are many extremal examples. Actually, all of the known extremal examples indeed are F1, F2, and F3 free. And okay, the best result in the direction for relaxing the conjecture is due to Jean-Sébastien Seremy, Rémy Dionys de Vercos, and myself, where we prove, using a little bit more of Fleck algebra applications, we push the constant below 0.34. Anyways, as far as the methodology goes in, I believe this is still very far from understanding what is going on. So, okay, now I want to go back to Caccetta-Haggkvist, and also to the fact, so the conjecture of Caccetta and Haggkvist was actually inspired by an earlier conjecture, which is actually weaker. And so in Caccetta-Haggkvist, you assume that your out degree is large, which, I mean, modulo flipping the orientation of every edge is the same as saying that your in degree is large, and then you want to find a cyclic triangle. So what if you assume both in and out degree are large? Does it make your life any simpler? Well, that's exactly what is the conjecture of Bézard, Chartrand, and Wall is saying. That goes to the beginning of 1970s, and let me now focus only on the triangle case, but really the story would be the very same as for Caccetta-Haggkvist in case of the longer cycles. It says that as long as your in and out degree, which I will like the minimum of the two, I will call the semi-degree. So as long as your semi-degree is at least n over 3, you should contain a cyclic triangle. And if you recall all of these constructions that I was presenting, they not only had a large out degree, but they also had a large in degree. So all of them applies, and the conjecture is, this conjecture in the, especially, or the triangle case of this weaker conjecture is as open as the Caccetta-Haggkvist. Okay. But if I don't go, so if I would generalize, if I would think of the full generalization of this, or of the full version of this conjecture, also for the longer cycles, it's always trying to find a cycle of length at most. It's only the triangle case where it's really some degree threshold implying existence of a cycle of a particular length. So that sort of, so this direction of thoughts and this conjecture of Bézard, Chartrand, and Wall, they inspired Kelly, Kuhn and Osthus to ask, okay, so but if I care really about the cycle of a given length, not of a length at most L, but really L, what can I say? So they could say a lot. They, for example, show that as long as your cycle is not triangle, and maybe also as long as your starting graph G is sufficiently large, then if you take an n-vertex oriented graph where all the out degrees, or well, all the out degrees and all the in degrees are strictly more than n/3, you find a copy of a cycle of your favorite length. And the dependency here, this n0 here indeed depends on what L you want to find. And if the length of the cycle you care about is not multiple of 3, then it's best possible because you just take a blow up of a cyclic triangle, and all the cycles all the oriented cycles you can find there must indeed have a length divisible by 3. So for such value of L, this is indeed the best possible result you can hope for. Are there any questions? Okay, so when L is not a multiple of 3, this is indeed best possible, but you sort of feel that if L is actually divisible by 3, this construction indeed contains a lot of those copies, and one would believe that, okay, in this case you can do better. For example, when L is 6, when you look for C6, of course you find it here, and it seems to be hard to just a little bit alter this construction, so a little bit shift the out and in degrees down to avoid having the C6. So that motivates the following definition, and also, okay, let me first tell you the definition. So for given an integer L, by KL I will denote the smallest integer that is at least 3, which does not divide L. So for example, if L is not divisible by 3, then KL will be 3. But for example, for L being 6, KL will be 4. Okay. And now, a way how to, definitely a way how to avoid having an L cycle would be to take a blow up of a cycle of length KL. Because, so for example, when L is 6, I would take a blow up of 4 cycle. Because there all the cycles I would ever be able to generate must be multiple of 4. But I cook up KL in such a way that it's not divisible, that L is not divisible by KL. So, for example, 6 is not divisible by 4, so in this I will never find an oriented 6 cycle. And then the conjecture of Kelly, Kuhn and Osthus says, okay, this should be the best possible. So as long as you can beat the minimum in and out degree given by the blob of the KL cycle, you should be in a good shape to find an oriented L cycle in your graph. And in other words, one can rephrase the theorem from the previous slides of Kelly, Kuhn and Osthus that this conjecture is indeed true for KL being 3. Also, in a later work, Kuhn, Osthus, and Pickett show the following statement. So, again, I will sort of look at the same problem from a different angle. So here I was fixing L and I was cooking up KL that is good for it. Now let me think, I will fix KL and I will start thinking of the length of the cycles, for which KL will be the value that I now put into my mind. So, for example, if I think about 4 cycle, I will think about all integers that are multiples of 3, but they are not divisible by 4. And then what they showed it, for whatever value k, which will be the value KL, as long as L is large enough, so as long for K being 4, as long as I take L which is multiple of 3, but not divisible by 4, and L is large enough, I will be in a good shape and the conjecture holds. And let me emphasize, it holds asymptotically. So maybe I need to add some epsilon n to this bound. Okay. So in the talk today, I want to focus on, so I want to do two things. I want to focus on the case when L is equal to 6, but at the end I will also say something about the other lengths, which, of course, the value L large enough for K equal 4 was something exponential in K, and L equals 6 was not covered by the original result. But I also want to convince you that this was really the most difficult case, at least from the asymptotic point of view. And the reason for that is that, the reason for that is following. So I will convince you about the 4 cycle being morally the extremal example, but you can do more in this case. You don't need to go just for 6 cycle, as long, which in other words, I want to convince you that the threshold is indeed what the blow up of 4 cycle is saying for C6. If you take a blob of 4 cycle, you go to one of the blobs, and inside one of the blobs, you put a bipartite graph, which is oriented from one side to the other. You create some 5 cycles, but you do not create any 6 cycle there. Also, you do create 9 cycles, because you can go 5 and 4 and loop another 4 cycle on top of it again. So this is really a feature only of being a blow up of 4 cycle and shooting for a 6 cycle, where you can mess up like this. For all the other numbers, you have enough freedom to loop around such that such a damage would actually make CL being present. So, and now, like, you can think of very many possibilities. I mean, any bipartite graph that lies here and has edges oriented in one way could be planted there, and so in this way you can construct, again, exponentially many constructions where which would be tied for this result, or which are actually tied for this result. So that's sort of my intuition why this was really the most difficult case. And also, I mean, the conjecture of Kuhn and Osthus was the general one, but at many occasions they emphasized this particular problem for L being 6 as the very interesting one, and they stated it as a conjecture of its own. Is there any question? So if not, let me also put here a stronger version, which is stronger in the same way as Caccetta-Haggkvist was stronger for the Bertrand Wall and one more name that I now cannot recall, conjecture, which would be just assuming that your out degree is as large as the blob of KL cycle is saying. Is that sufficient to make to contain an oriented cycle of length L? Okay. So if that, so I will not be really able to say something to really prove this stronger conjecture or claim anything towards it, except one thing that will appear right now. So anyway, so let me now sketch you our proof for how we are proving that the threshold, the semi-degree threshold for C6 is indeed 1/4. So let's start with a large graph G, where all the in degrees and all the other degrees are larger than quarter. And now I want to convince you, okay, you can find a C6 there. So let me start with an auxiliary claim, which is actually trying to prove something about the stronger version. Unfortunately, I would not be able to use this stronger claim for actually proving the stronger conjecture, but it would be a good tool for me to prove the weaker conjecture. I will try to explain it, but I'm now like trying to prepare you for the story. So the claim says that if you have a large oriented graph H, where the out degrees are at least 26%, you would contain an oriented C6, which, I mean, if I take the contrapositive of it, if you have a oriented graph H with no C6, then you must have a vertex of out degree strictly less than 26%. And the reason why I want this stronger claim is that the very same, I mean, if I now just say I want to assume only in degree, then again, I can flip the orientation of every edge to also conclude that all the in degrees implies the existence of C6, which from the contrapositive says, if I have no C6, I have also I have both vertex of low out degree, but also a vertex of low in degree. Okay. So all of that I've done under assumption of having no C6, but modulo may be doing some epsilon delta gymnastics by triangle removal, and I can also assume that there is no cyclic triangle. So let me not go into that then. Just
how much does the cyclic triangle cost you, epsilon n?
I will tell you only by the end of the talk. But right now, yes. Yes, right now, yes. Okay. So I'm saying that this claim has a very nice corollary which says that the diameter of the graph G is rather small, or actually even something stronger. For any two vertices S and T, you will be able to find an oriented path from S to T of length at most 5. So let me now show you a proof or sketch of the proof for this corollary. So you start with two vertices S and T, and okay, so and just to avoid at least for myself, to avoid confusing myself, I'm now trying to show something about the graph G. And the claim on H will only be a tool that I will use on the way. So I have my graph G where all the in and out degrees are at least 25%. So let me look at out neighborhood of S, and it's at least 25%. And sort of symmetrically, skew symmetrically, let me look at in degree of T. But now, now let's look at the out neighborhood of S. That's a C6 free graph H, so I can apply the claim there to find a vertex of out degree inside here being rather low, being at most 26. I mean, if you at most 26 over 100 inside a block of size 25 over 100. So if you do the math, it's absolute out degree spent that is being spent inside this block is rather small. It's at most 6.5%. But that means that at least 18 point, one can compute these numbers online, at least, which I believe 25 minus 6.5 is 18.5, at least 18.5% of the out degree of this particular blue vertex must be spent somewhere else on this picture. Okay, it could be in principle spent here, but then I would have a short path and I would be already done. So let me assume it didn't happen. And from the symmetric point of view, I will find a vertex that has rather low in degree inside this, which means that it must spend some in degree also somewhere else. And again, if those two blocks overlap, I would already have a path of short length, and I'm done. So at this whole left side, take it as our graph H. Again, it's C6 free. So we must have a vertex that spends there at most, and okay, 25 plus 18.5 is 43.5, and you take 26% inside there, and the mass says that means that at most in the absolute numbers, less than 11.5% of the out degree of this vertex is spent inside here. But also look, already on this picture I have 25 and 25, that's 50, 18.5 and 18.5, that's 37. I have 87% of my graph already drawn here. This one has spent at definitely much less than 12% of its out degree here. It can maybe fully be connected to those 13%, but its out degree in total must be at least 25. So he must send something out, something to the right side of this picture. But then I have path of length at most 1, 2, 3, 4, 5. Okay, and that's what I'm doing. And I should emphasize here, or before that, are there any questions about the proof?
You don't need the full 0.26, do you? There's a little bit of overlap.
Oh yeah, and also I can do, to some extent, this 26 I put here. I can do much better number there, but I put a number so
To
that
get
the
the
math,
corollary as well.
so the math is nice on the slides, but we have much better estimates and we have much larger overlaps if we really need.
Okay.
But at least for the purpose of this control, we don't. So already this is sort of hard math for me to do online. So I don't want to make it even worse. Anyways, so I should emphasize that this was like it's so much tempted to say that all the time I was sort of using. I mean, I was applying sort of a very similar statement about a subgraph. Then why am I really doing this detour and not just proving my favorite theorem by induction? The trouble is that if my theorem that I'm trying to prove by induction, I would be proving the weaker one, then I cannot really order here an out degree, and maybe the induction hypothesis gives me in degree, which completely ruins my plan of going this direction. Or if I would be proving the stronger statement, then I would not be able to poke induction hypothesis for. Oh, sorry. Then
the right-hand side.
then I would not be able to go this on the right side because I would be only getting out degrees. So it's really that those two things should have been interleaved in this way, and the only conclusion I can get out of those two is regarding this weaker one, where really my hypothesis about G is on both in and out degree. But so what is this corollary used for? Well, for corollary prime. I'm claiming that just using this we can show that each out neighborhood and symmetrically each in neighborhood in G must be acyclic. Well, why is it so? Actually, even something stronger. No neighborhood can contain a path on 3 vertices. Because if you would have a path of 3 vertices, then so path x, y, z inside W, then you just apply this corollary to go from Z back to W in length at most 5. And if you go through all the possible cases, you will always end up in having C3 or C6. But then, corollary double prime is that actually, so by the way, look that actually if you think about the extremal example, this is not tight. Between any 2 vertices you can go in at most 4 steps in blow up of C4. Also, this claim was not really tight. But we use those 2 steps as a bootstrap to actually show that indeed the diameter is at most 4, or between any 2 vertices you can go in at most 4 steps. And now, having this result, this is really easy. You just repeat this argument. So you now know that each in and each out neighborhood is acyclic. So start doing the very same picture, and first go for your 25%. But now, the way how you choose the vertex, how to continue in this block, is not that you take something guaranteed by the red claim. You just take a sink in this block. A sink means that it doesn't have any edge going out, and every acyclic graph has a sink. So that means that it goes outside by not by 18.5, but actually by 25 again. So you go 25, 25, 25, 25, and if your out degree was actually more than 25, you kind of either constructed an oriented triangle or you really constructed a blob of C4. That maybe requires a little bit of reasoning, but from this it really follows in a sort of straightforward way. Okay, that's what I just said. So is there any question? So the only mysterious thing is this red claim, which I guess I can see Bernard sort of smiling. This is really a claim that you can ask. So it's a claim that it should not be tight, and I mean, if you believe in that stronger conjecture, it is not tight. But it's something you can ask this flag algebra framework to prove for you. And indeed, if you ask them in a sort of straightforward way, you get something. You do not get it down really to 1/4, but you get definitely something of 26%, or even something much better. 25.1 would be also doable. Okay, so what is this flag algebra framework? So I won't be really able to tell you all the nuances and details about it, but let me at least, for those who knows this framework, I guess this will be a rather boring slide, but for those who don't know, I will try to give you like sort of glimpses what this framework is doing and what one could sort of expect, what one could expect to use it for, what one can expect to be useful for. Okay, so it's a framework which was developed by Rasborov, and it's sort of trying to give you a systematic approach to problems in extremal combinatorics. And if I would really try to compress all of this into one sentence, I would say you are trying to analyze properties of large graphs, or maybe large dense graphs, using the relations that you can observe between small graphs. And sort of like, it's hard to look at a large graph, but it's not that, it's sort of much easier to be spotting out relations between graphs of size 4 and 7, for example. Even like if you do some exhaustive analysis, you can really understand how those two graphs relate to each other. Okay. So rather than trying to say more general blah blah, let me show you an example. Or let me show you an identity first. So I'm saying that for every undirected graph G on n vertices, there is an identity, sort of a crazy identity, which says the following. So up to lower order terms, I'm saying that in any such n-vertex graph, if you take n times n squared minus 4 minus number of edges, it's essentially equal to the number of induced subconfigurations of this type, plus 3 times the number of triangles, minus 3 times of triangles, plus this funny sum where you take n½ minus the degree square and you sum over all vertices. It's sort of a crazy identity, which, I mean, right now it falls down from the blue, out of the sky. And let me emphasize 2 things. So first thing is that, actually, if I tell you this identity, I send you home. It's really an exercise in double counting for, say, 15 minutes to indeed prove this. So proving this identity is not that hard. And I'm also saying that apart from being a double counting exercise, there is actually maybe some deeper meaning behind this. And now, okay, if you do know what flag algebras are, I ask you to not answer my question. But if you haven't seen this before, let me ask you, would you have some sort of useful meaning for this apart from being an exercise for double counting?
Look at it as a neighborhood kind of restriction. You look at neighborhoods of vertices, and you say something about what can happen inside them. That's what the n times non-edges says to me.
Mm-hmm. Maybe. Okay. This is always this thing like, here is a theorem, try to deduce from it something useful. Well, anything that is true, you can deduce from something that is true on one hand, as one of the steps. But I promise that there is some short answer for my puzzle. And from my point of view, it might be sort of simpler than what you are trying to juice out of this now.
Is that something to do with the number of triangles within a graph, or some kind of?
Okay, so you can definitely get out of this something. You can get out of this some bound on number of triangles.
Yeah.
But if we are counting triangles, have you seen this? Have anybody seen this n squared over 4 somewhere? Well, I'm saying that this is a one line proof of Mantel's theorem, or maybe to be less sketchy, it's a like one line recipe. You still need to do this double counting. But once you have this identity, once you believe this identity, proving Mantel's theorem is really trivial. Because if your number of triangles is 0, then I'm saying that the left-hand side of this identity is trivially non-negative because, okay, number of some configurations, no matter what the number is, it's counting something, so it must be non-negative. Here I'm taking this crazy sum of n½ minus degree, but I'm taking square of it. So I'm summing some non-negative numbers. So on one hand, the left side of this identity is non-negative. On the other hand, if I look what it means for the right-hand side to be non-negative, well, then better the number of edges is less than n squared over 4. So what Fleck algebra, or what one particular tool from Fleck algebras is trying to do, well, it's exactly trying to, given your starting problem, like what's the max number of edges in a triangle-free graph, it tries to cook up an identity of this form such that it would witness what you are trying to prove. And this turned out to be pretty useful. And here I put just few other applications than just yet another proof of Mantel's theorem, which were not known before, and they were obtained using this framework. And I should emphasize, this is really not an exhaustive list of the application, and it's also not trying to show the most interesting ones. I would say they are just trying to show the nice, that can be quickly written on a slide with a nice picture accompanying it. So, for example, there was an old question of R', what's the maximum number of pentagons in a triangle-free graph? It was conjectured the number should be as many as you would have in a blow-up of C5, and that's now a theorem. There is some similar, at least spiritually similar question in oriented graphs where you are trying to maximize the induced out forks, and then the answer turned out to be this sort of fractal-like looking structure where the parts are appropriately balanced, and actually the ratio between them is irrational. Or yet another problem is some sort of a strengthening of R'-Sekerash lemma, which would be saying, oh, in every permutation on k square plus 1 points, you would have either monotone increasing or monotone decreasing sequence of length k plus 1. So instead, if you just care about the existence, you care about what's the number of them. And again, to some instances of this kind of question, the framework can be, for the Fleck algebras, those are sort of the questions of the same spirit, and to all of them, you can check whether this framework can say something meaningful or not. And it turned out that in those instances, it indeed does. So, like, if you go a little bit far and you stare at those couple of examples I put here, it shows that, what's trying to be done is that you are trying to solve an instance of a problem where you are maximizing over, say, all large graphs G, number of copies of some favorite graph H, or maybe some combinations of graphs H in G, subject maybe to some constraints on G, like being triangle free. So it would be really awesome if this Fleck algebra framework would be just like, okay, that's a hammer to questions of this type. Unfortunately, this would be maybe too much to expect. And actually, if you would go from this optimization problem just to its like decision type of weakening, when you would be just asking, oh, giving a combination of graphs, if I go over all graphs G, is it always non-negative? Just this decision problem is actually algorithmically undecidable. So there is kind of like there is a strong no hope suggestion that you cannot have a general hammer to this optimization. But what Fleck algebras are proposing, okay, let's try to do something else. So we have an optimization problem. It's provably hard, but let's consider some of the relaxations, and let's maybe hope that we take such a relaxation that it would not change the problem too much, and actually maybe so it will not change the problem much, and the extremum points would still stay the same. But on the other hand, it would move us to a subset where we know how to do the optimization. And indeed, that's what Fleck algebras do, and they suggest, or the semi-definite method does, and it suggests some particular semi-definite relaxations. And if you know a little bit about semi-definite programming, here on this example, I was trying to find some sum of squares, and finding some combination of sum of squares and semi-definite programming. That's really something that is tightly related to each other. And so, and so from the SDP duality, the relaxation really nails down to finding sum of squares that is proving the given inequality. And the punchline here is that maybe modulo some technical details, and those technical details can be really annoying, but let me not address it now here. Such search of those sum of squares could be computer assisted, and you can actually ask a computer to generate you a proof that conceptually still looks like this. So conceptually, if I just give you the identity, it's an exercise in double counting to prove it. However, this could be very long. This could be very lengthy. It could have a couple of the description itself could have a couple of megabytes, and it's sort of, I guess it's sort of too much to ask from a human being to find this by hand. Okay, so this is sort of like a crash course to flat algebras without actually really saying what has happened. Anyways, is there any question? Okay, if not, let me actually move to the question you asked me a couple of minutes about. And what is the exact value of this semi-degree threshold for C6? So here I wrote down the general conjecture of Kuhn and Osthus, and they really stated it in this way, in this precise way. So if I plug L equals 6, they said that as long as your out degree in and out, all the in and out degrees are more than n over 4 plus 1, you should have a C6. Okay. So I want to say that actually this is false, and you can do a little bit better. So, and let me now try to do some damage to C4 to convince you that you can do a little bit better. So so what I'm gonna do, I will give you a graph where the number of vertices n is congruent to 3 modulo 4. So n over 4, or in other words, it will have n plus. So if this one has n vertices, I will add 3 more vertices to it. So it will have n plus 3 vertices, which from the point of view of this floor is really the same. But I would be able to boost each in and each out degree in this picture by 1, and still avoid any 6 cycles. So I put 2 vertices in those blobs, in 2 blobs, and now I could observe, okay, so that means that I already boosted all the in degrees here, all the out degrees here, all the out degrees here, and all the in degrees here. So each vertex in each blob is missing one of the types. So let me assert vertex that does the appropriate job for everyone. In this way, I of course create a cyclic triangle. Also, I create C5, I create C7 there, and so on. But still, there is no way how we can find C6 there. However, I boosted the semi-degree by 1. But what we can do with Roman and Andrzej is to show that, okay, as long as you go 2 by 2 above, you do contain C6, and now actually in the proof we don't use the removal lemma because of course that would be too coarse. So we need to be more delicate in many places, but we can.
Well, you could probably do a bootstrap where you do triangle removal, and then it works unless everything's very nice. But I guess. But
the trouble here is that the structure is not very. I mean, I can imagine that sort of, or at least that was our first hope that it would really go sort of from some sort of stability point of view.
Right.
We are not sure whether you can really do it. Partially because that's actually the reason why, that's actually the way how we observe that such small damages can happen, and now it starts really being annoying because you can have something maybe planted here, you can have maybe one. We rather worked hard to avoid the removal lemma, and this is what it is.
Okay. Did you know this example in advance, or did it drop out of the proof?
No, it dropped out from the attempt of the proof, where we really tried to do just +1, and we were maybe even able to do +2, and then we were thinking how to go down from +2, or went from plus constant to +1, and then it popped. Okay.
Is this optimal in the sense that if you go through all the divisibility classes of n, that you have the most precise answer?
I hope that nobody asked me. So, okay, I guess I can do actually a little bit better. Okay, so I'm pretty positive about this one, and I believe we can actually change the floor to ceiling, which means that if n is actually divisible by 4, you don't lose one.
Right.
However, this picture we can really do only for n being congruent to 3. So maybe this really fails only when n is congruent to 3 modulo 4. And so to some extent there is maybe still the congruence class n is congruent to 1 and n is congruent to 2, where we haven't really nailed it down to this ±1.
So I wouldn't say the conjecture is false, it's just slightly false.
For every n congruent to 3. That's still a lot.
Well.
No.
False at least a fourth of the time.
Okay. And so for the other length of the L, now it's sort of, I mean, you can sort of do similar kind of damage to also longer cycles for the value KL, as long as the L modulo KL is appropriate. For example, this damage would not really work for, I believe, C9, because I created a 5 cycle and I also can loop a 4 cycle on top. But as long as L is congruent to 2, this damage works. So the similar kind of conditions we can also do for other cycles. So I mean, that means that the conjecture is sometimes true, sometimes, or at least it's not disproven sometimes, and it's disproven. I mean, but if you just want a general statement of this type without like really considering if n is congruent to something modulo k and L is congruent to something modulo k, it is for every class k.
No, I just, there was a theorem that I was dealing with a conjecture that was only false when n was an odd multiple of 3 and only in one actual unique case.
Oh, okay.
So that's where I
no,
slightly
but,
false.
so this is a little bit more false. It's 25%.
Okay, very good.
Which I don't know whether it means something, whether this 25% is related to those 20, I guess. Okay. So just to conclude. So there was this general conjecture, or so far there is, but in a second there was a general conjecture of Kelly, Kuhn and Osthus about the semi-degree thresholds for finding oriented cycles, where as long as your cycle is not triangle, which is believably the hardest instance of Caccetta-Haggkvist conjecture, they provided that the picture should be sort of the picture should be following this blow up of the shortest cycle, avoiding presence of CL. That should really give you the extremal example. So, and Kelly, Kuhn and Osthus prove it for KL being 3, and then there was also the asymptotic result, and now it makes sense that it was only asymptotic result of Kuhn, Osthus and Piquet. So what I showed you today was the case, was the proof of the conjecture with the appropriate fix for L equals 6. And also, what we can do, we can actually, at least asymptotically, we can really solve the whole problem. So as long as we can allow ourselves epsilon times n like in all the in and out degrees, we can indeed show the full conjecture. And now it comes again to this, like, if we can get from this sort of like a stability that would bring us down to the actual solution. It feels we can, but not sure whether we can really get here just this +1 or +2, or if we can. So far it seems we can get there some constant, but this constant will depend on k. So
No, that's all right.
Yeah, it's still okay, but it's just that it's not like fully finished and we are still not sure what would be the function we can get, and there is still some work on progress. On the other hand, I want to put here the stronger conjecture where you assume only one side, let's say the out degrees being large, and that's still a conjecture that is widely open, I believe, for every L. Even if you try to do some Kuhn, Osthus, and Piaget kind of statement where you assume that L is large and you know what K should be, still, I don't think there is any result in this direction. Just simply because it's really hard to have only bound on one of those degrees. But I mean, in their proof, they also sort of try to build short paths from both of the directions, and all of those arguments sort of fell apart when you have only one-sided bound. Okay, so with this, and with the fact that I'm slowly going to the end of the, or quickly going to the end of the 1 hour, I want to thank you.
More questions? Already got many questions during that.
I'm sorry.
No, that's good, that's good. Let's thank the speaker again.